Hi, welcome to this new video on kinematic indeterminacy of frames. Now we are familiar with what is meant by kinematic indeterminacy, so I'm not going to repeat the definition. Fine. Just I would briefly say it's all the degrees of freedom that are required to every joint. When we sum them up, we get a kinematic indeterminacy. And figure 1 and 2 shows what are the degrees of freedom we consider usually for a truss element and a beam element. Here we have a truss element wherein we require two translations at every joint, and for a beam element we require the transverse degree of freedom, that is transverse displacement, which is along the y direction, and then the rotation about the z axis. This is what it takes for each joint of a frame element, sorry, beam element. Fine. Now we are here to see what it happens with a frame element. I have taken the typical frame element here, which contains two elements such as AB and BC. I'm just showing this element BC here. So at every joint, these three degrees of freedom should be taken into account when it comes to a frame element. That is translation along x direction, translation along y direction, and then rotation about z axis. Okay. So here we see that at joint C as well, I'm showing all three of them. Overall, what I can say here then is 1, 2, 3, 4, 5, 6. So in this case, the kinematic inertia will be 6 because it's a fixed joint, so no degree of freedom should be taken into account. But for a frame element, it is possible that we can ignore axial deformations. Right? In beam element, we always ignore axial deformations, but for a frame element, we have a choice. Because for certain problems, even if you ignore axial deformations, the end result is not going to differ significantly from considering that. I mean, considering axial deformations being there. Okay. So it depends. We'll see two categories of problems. But just for demonstration's sake, I'm saying here, if in this case, the axial deformations are ignored, what it would imply is for this particular element BC, U2 should be equal to U1. Only then this member can't change its length. Okay, only then we can also say axial deformation is negligible or zero to be precise. Okay, so for element BC, U2 minus U1 should be equal to zero. What about the element AB? This is a fixed support, but this degree of freedom is usually there. If it is there, it means that this member undergoes change in its length. So this shouldn't be there if we are ignoring axial deformations. Therefore, this particular degree of freedom V1 should be 0 for the element AB. All right. Hope it gives some idea about what it means by ignoring axial deformation. Anyway, we'll take up more problems later and see how it affects the kinematic indeterminacy. Now, just a quick recap of what are the degrees of freedom that should be taken at every support as well as certain joints. Okay. Now, when it is a fixed support, all three degrees of freedom wouldn't be there because these translation rotations are restrained. So, 0 is the degree of freedom which should be taken for fixed support. Then for a pin support, this rotation alone is permitted, which means the degree of freedom is 1 for a pin support. What about a roller support? It allows translation this direction along with the rotation. So the degrees of freedom is 2 for every roller support. And what about a guided roller support? This allows only the translation along this direction. Hence, 1 is the degree of freedom. What about a free end? At a free end, all three degrees of freedom are possible, such as true translation and rotation. Hence, the degree of freedom for every fixed free end is 3. And even if you have a rigid joint, something like this, here also these three degrees of freedom are permitted. So for rigid joint also, we consider the degree of freedom as 3. How about a moment release axial efficiency release? Whenever you introduce a particular release, what it does is it disrupts the continuity of the kinematic entity associated with what you are releasing. That means, for instance, if I introduce an axial release here, it doesn't permit the axial force to be transferred from this part of the structure to the other one. That is, we say the axial force is 0 here, right? Just similar to what happens with the moment release. Then the kinematic quantity associated with that is the displacement along this direction. So the displacement along x direction is no more going to be single valued at this location. Hence, you see that just to its left we mark u minus and just to its right we mark u plus. However, the other two entities will be single valued. That is, the displacement along y-axis doesn't have two values. Similarly, the rotation is also single valued here. We have seen this already in case of a beam, okay? But when it comes to frame, this is also taken into account. That is, for a beam element, we said this, this were possible, but for a frame element, these two translations will be single valued. However, the rotation will be double valued. Fine. Similarly, for a shear release, as we are releasing the shear, this y displacement will be double value, but the other two entities will be singular, the other two kinematic entities, I mean. Okay. So you can see that for each case, we need to consider a degree of freedom 4. Usually, if you take a particular rigid joint, only 3 of them are possible because of the release what we are introducing. One of those kinematic quantities would be double value and hence 4 for each case. Okay, that's all. We'll directly see some problems. This first problem, we have 6 joints. We'll go joint by joint and quickly we'll summarize what is the kinematic indeterminacy. This is a fixed joint, so 0 degree of freedom. These 4 are rigid joints, hence 3 degrees of freedom permitted for each of them. Okay, finally, this is a guide roller support. So only this displacement along x-axis is possible, hence 1. Sum them up, 3 times 4 plus 1, 13 is the kinematic inertia for this frame. The second problem, we have a moment release at this location C. This is a fixed joint, so no degree of freedom. This pinned one, so only rotation is possible and hence 1. And this particular joint is a rigid one, therefore 3. How about this joint C? Here the displacements will be single valued because it's a moment release. It is going to cause the rotations which are, which the rotations associated with this beam and column to be different. Okay. Otherwise, this being a rigid joint, the rotation will be same for the beam as well as column at this end. However, because of the introduction of this moment release, they are going to be different. So we need to treat them independently, and hence theta b for beam and theta c for this column are marked here. So overall, 2 for this transverse displacement which are singular and 2 for the rotations which are double valued here. Sum them up, 3 plus 4 plus 1 gives a value of 8. So kinematic inertia for this particular frame is 8. This third problem, we have several joints, but we can easily categorize them because this joint J, joint K, and joint G are rigid joints. So at each of them, 3 degrees of freedom are possible. So I mark 3 everywhere. And this is a free end. Therefore, here also we expect or we should have 3 degrees of freedom. How about the joints? This is a fixed support, so no degree of freedom. Here this is a pinned one, only rotation, hence 1. And this is a roller support, so this plus this are possible 2. How about this moment release here? Here we need to be very careful because this is associated with all these 4 members, right? In case of static inertia, we have said that because of introduction of this, it is going to give us n minus 1 extra conditions to solve for the unknowns. If n are the number of members associated with this internal inch. But this kinematic inertia, what happens when you introduce this moment release here is each of this member, all if you consider FE, FJ, FG, and FC, each of them will have the freedom to rotate independently at this end. If this is not present, if this moment release is not present, all these members will have the same rotation at this end because this will be a rigid joint. However, because of this introduction of moment release, all these rotations are going to be different here. Therefore, 1, 2, 3, 4. So this 4 is to account for these 4 independent rotations possible here, and this is to account for 2 translations which are however single value, right? So what remains is just sum them up, you get a value of 36 for this frame. So the kinematic inertia for this frame is 36. The next one contains a gable frame, but with a moment release at this ground location C. Just this is a fixed support, so no degree of freedom permitted. Here this is a rigid joint, so 3, 3. But here, because of the introduction of internal hinge, this member will have a rotation at this end different from this member. So this two is for those two slopes which are different, and this two accounts for what? The unique translations that are possible here. So again, 3 plus 4 plus 3, 10. So 10 is the kinematic inertia for this particular frame. 10. Okay. And we have the last problem here, which contains all three releases. So we need not bother about these rigid joints much because all of them permits 3 degrees of freedom. So 3 marked everywhere. And this is a fixed support, no degree of freedom. And this is a guide roller support, which permits only this translation and so on. Just we need to have a look at these releases here. This is a moment release. So which means this, this, sorry, I'm following anti-clockwise. This is the positive one for rotation moment. So these are the degrees of freedom here possible. And this is shear release. Therefore, what should happen here? This is unique. This is unique. However, this and this will be not same. So 4 degrees of freedom here. This is a axial release. Therefore, this and this will be different, and then these two are unique here. Okay. So for each of them, 4 degrees of freedom will be there. All right. Just sum them up. You get the value of 37. So 37 is the kinematic intensity for this particular frame. That's all. Thank you so much. In the next video, we will see some examples wherein we consider that axial deformations are negligible and then see how it affects the kinematic intensity. All right.